Okay, so today we're going to be looking at the intermediate value theorem and also talking about limits at infinity. Okay, we didn't quite get to finish up the section there on what is this here? 2.4. Okay, like on continuity and one-sided limits. That's what we're going to do right now. We kind of left things off right here at this intermediate value theorem investigation. Now, this is already filled in because my original video did not record, and so I am redoing this, but hopefully with more brevity and just kind of compacting things together. Anyway, so the intermediate value theorem is one of those kind of big concept ideas that we want to have down in preparation for, both, of course, upcoming tests, but also the AP Calculus test. It's one of those big ideas, kind of like continuity is a big idea that we should be familiar with, and the three criteria necessary for, something to be for a function to be continuous at a point. That is, the function existing at that point, the limit of the function existing at that point, and then as x approaches that point, I should say, and then also the function and the limit having the same value as well as x approaches that point, or when x is at that point. Those kind of things, right, that's a typical kind of like justification we may need to be able to give at a given time for a given function, and so we want to be prepared for that. All right, a lot of the math that we're used to doing, right, is like I give you a problem, I show you kind of like the steps to solve that problem, and then you provide a solution. But sometimes, every once in a while, we have to understand these kind of like big picture ideas. Continuity is one of them, and intermediate value theorem is also just an important theorem to use and have down so we can use it to justify, an answer for a particular kind of problem. So, that being said, intermediate value theorem is something that we've kind of already talked about. It was like on the last homework that we did, the homework that was from one-sided limits and continuity. There was like the very last question where you were asked, how you could know whether your function will hit a certain value, and you're given on a particular interval. So you're given like two endpoints of an interval, and it turned out that one of those y values at the endpoint was below was maybe like in the negatives, and the other endpoint, its y value was in the positives, and so since the function was also continuous, that you had to hit all the numbers in between, including 0, for example. If you go from negative to positive, you have to go through 0. And that's kind of the basic idea about the intermediate value theorem. All right, if we look here at example 1, all right, we're considering a function, x to the fourth minus 6x plus 2, from the interval 1 to 2. Okay, we're asked to find the values of f of 1 and f of 2, which I did right here. There's f of 1, there's f of 2. Okay, you can see f of 1 yields negative 3, f of 2 yields 6. And I plotted those points right here and here on my graph. Explain why, then, f must cross the x-axis between 1 and 2. And here is between the x values of 1 and 2. And here's kind of the main idea, right? At x value of 1, we have a y value of negative 3. And at x value 2, we have a y value of 6. All right. Since this function is continuous, right, there's no need for us to really discover, look at the discontinuity. There are no discontinuities for it. Since that's the case, we know that the function's got to get from this point to this point, right? And it's got to go through all the y values in between. So certainly we'll not only cover 0, but we'll also hit, all the integer, all negative 2, negative 1, 1, 2, 3, 4, 5, and all the numbers in between there too. Okay, so we've got to get from this point to this point, so every y value is going to get hit. And that's essentially what the mean value theorem says. Okay, given a continuous function on an interval, then we can find we can find an x value between our two x values in our interval that would then yield any y value between the two y values of our given interval there too. Okay. So in this case, we say since f of x is never discontinuous on the interval from 1 to 2, and negative 3 is less than 0 is less than 6, again, the negative 3 and the 6, that comes from f of 1 and f of 2, right? So that 0, that y value we want to be certain that we hit, or I guess the y value that we want to be certain that we equal here is 0, right? We want to know that we do have a 0. It's between the y values of our two endpoints. And so certainly we've got to go through 0 to get from negative 3 to 6, right? So then I say, then f must pass through the x-axis or have a y value of 0 at least once on the interval from 1 to 2. So that's another key thing too. Not only do we guarantee that we must pass through 0, but it could happen more than once. Okay, we don't know that, but at least once we've got to go through 0 to get from -3 to 6. All right, then I had students do number 2 and graph this one. It's piecewise, right? So we do have the opportunity here for it to be discontinuous. However, the individual pieces are never discontinuous, and at 0 it does join up, so we don't have anything to worry about there. The function is continuous. The question here now is not, must the function equal 0? Must there be some c value between x equals -3 and x equals 2 such that g of c is 3? So now we're saying, must our function be 3 at some point? All right, so we do the same kind of process we did before. At x value of -3, we have a y value of 11. At x value of 2, we have a y value of 0. So we're going from 11 to 0. Since 3 then is between 0 and 11, then yes, we are guaranteed that g of c, there must be some c between -3 and 2 such that g of c will then be 3, because again, that g of c, the y values are between 0 and 11. So again, maybe an easier way to say it is there must be some x value between -3 and 2 such that when we do g of that x value, we'll get somewhere between 0 and 11. Okay, and so that includes the 3 then. All right, then we go to the next question though, must g of c equal -8? Right, and the answer here is no, we can't guarantee that. Our highest y value is 11, sorry, yes, our highest y value is 11. Our lowest y value that we see is 0. So we can only guarantee that we will be between 0 and 11. -8 is outside that range, and so we cannot guarantee that the function will be in between. Well, the -8 is not between there. It's not an intermediate value. It's outside the 0 and the 11, so we can't guarantee that. Okay, -8 is not between. G of -3 equals 11. G of 2 equals 0. All right. And then we have one more here, number 3, okay, where we have a discontinuous function. Again, graph the piecewise function. We found the values of h of -3, it's 11 again. Found the value of h of 2, it's -4 now. And then the question is, think about whether h of x will take on the value of 0 somewhere in the interval. So does our function have to equal 0? And you, again, using our previous arguments incompletely, we might say, oh, well, high 11, low -4, so we're going from 11 to -4. Well, we've got to get to 0 through 0 there. But when you look at the function here, you see that isn't so. And it's because we have a discontinuity there. So since h is not continuous on the interval from -3 to 2, then we cannot guarantee there is a c that's between that -3 and 2 such that h of c equals 0. Even though 0 is between the h value at 2 and the h value -3, it doesn't doesn't guarantee that we have to have a place where our function actually equals 0. And you can see it in the graph right here. Clearly the graph jumps. Okay? So again, that's the intermediate value theorem. We want to be able to justify that. So in summary here, here's the actual function. Suppose f is a continuous function, right? We went through that the intermediate value theorem to work, you have to have a continuous function on a closed interval from a to b. Okay? For any number k between f of a and f of b, so k is like a y value. This is like the number you're trying to prove your function must hit or must, equal. Between f of a and f of b, there's the intermediate part. K is intermediate between f of a and f of b. There exists a point c between a and b, the x values now, so an x value between these two left and right endpoints such that f of c equals k. Okay? In a picture, here it is. Here's kind of a nice continuous function with a and b, a going to then f of a, b going to then f of b, and you can see that if we pick some k value between f of a and f of b, an intermediate value, all right, then there is guaranteed to be some value c between a and b that when you take f of that c gives you k. Okay, a couple notes again. The intermediate value theorem is an existence theorem only. Therefore, you cannot use it to show what the value of c is necessarily. Now, obviously, in the previous examples where we did the intermediate value theorem applied, we could have figured out the exact c value, but that is not always the case. We can't necessarily say that, but knowing that something exists can be helpful as well. Also, if the intermediate value theorem fails, that does not automatically mean that there is no c value that gives you k, right? So again, something else to keep in mind. Some other things too, right? So for example, we can talk about a discontinuous function here, 1 over x, okay? Would the intermediate value theorem apply to this? Well, it depends. 1 over x is discontinuous at 0. Remember, for the intermediate value theorem, f must be continuous on a closed interval from a to b. This 1 over x is continuous on the interval from 1 to 2, so we could still potentially apply the intermediate value theorem there if we wanted to. Okay? It's only if our function is discontinuous on the interval that we have to concern ourselves. Here we see example 5. Okay? We're told that certain values of the continuous functions f and g are given below. So continuous, important that f and g are continuous. The function h is given by h of x equals f of g of x minus 6. And then just our question here, explain why there must be a value r for 1 less than r less than 3, so r between 1 and 3, such that h of that r is equal to negative 5. Okay, so here's our intermediate value we want to see if we can guarantee. So there's our interval a to b. Okay, so we will plug in 1 to our function here. We get 3. G of 1, if you use your table here, g of 1 is 2, and then f of 2 is 9. You can see the progression here, so we get 3. And then h of 3, by similar progression, gives us negative 7. Okay, now we can see that our values here are extreme. Well, not necessarily our extremes, but we have at the endpoint a 3 y value, and at the other endpoint we have a y value of negative 7. Negative 5 is between those two numbers, and so we can guarantee that there is then a r value between 1 and 3, such that h of that r would give us negative 5. Okay. So here's the explanation. Since h is a composition of continuous functions f and g, then h is also continuous. Important to note that. Since h of 3, which is negative 7, is less than negative 5, which is less than h of 1, which is 3, then by the intermediate value theorem, there exists an r, 1 less than r less than 3, r between 1 and 3, such that h of r is negative 5. Okay. All right, moving on to infinite limits. So sometimes it is useful for us to identify when a function approaches infinity, okay, when it doesn't exist and approaches infinity, as opposed, and which infinity it approaches to, just for like an idea of, I guess, what the graph looks like and stuff like that. Okay, so a limit in which f of x decreases or increases without bound, increases or decreases without bound, as x approaches c is called an infinite limit. Okay, so we look here at some examples. All right, we sketched some of them, and then we approached from the left and right of 1, left and right of 1, left and right of 1, left and right of 1 to evaluate those limits. Okay, you can look through there. I don't really think there's an explanation needed. You can just kind of see visually what's going on with those infinite limits. Okay. At the bottom here, a little summary here. If f of x approaches infinity or negative infinity as x approaches c from the left or right, then x equals c is a vertical asymptote of the graph of f of x. So this is important. We can have another way to kind of identify vertical asymptotes, right, using limits. If a limit from the left or from the right approaches infinity or negative infinity, then we have a vertical asymptote at that actual location. Moving on. Okay, vertical asymptotes are non-removable discontinuities. Again, no surprises there. We knew that. Therefore, the limit of these discontinuities, does not exist, right? That contrasts that with removable discontinuities like holes, where the limit does exist at those discontinuities. So removable discontinuities, their limits will exist as you approach them. Non-removable discontinuities, their limits will not exist. They'll go to either positive or negative infinity. Here's an example of just, again, application with this, stuff we've seen before. Determine all discontinuities of this function, then compute the limit at each of the domain restrictions. So we identify the domain restrictions. It's going to be positive and negative 2 because that's going to give us 0 in our denominator. But then it's a matter of discerning which one of these is removable, which one's not removable. If you look at the original function, okay, we can factor and cancel the x minus 2 factors there, okay? This allows us then to evaluate the limit as x approaches positive 2. And so therefore that limit will exist. It's going to be 3 halves, right? If you take the limit of this function as x approaches 2, all right, you'll be able to cancel out the x minus 2's and then direct substitute in the 2's and get 6 over 4, which is 3 halves. All right. Compare that, though, to the other discontinuity at negative 2. Well, again, we factor and cancel those x minus 2's, but if I plug negative 2 in, still I'm going to get 2 over 0, which is indeterminate form, or sorry, not indeterminate, undefined, right? And so we have a vertical asymptote there. Non-removable discontinuity at that negative 2. Okay. So that's all we were asked to do there. All right. 3, asked to find all the vertical asymptotes for this one. All right, again, vertical asymptotes occur where the function is undefined. So we're looking for when the denominator is 0. So you set the denominator equal to 0 and solve. You get x equals 0. Okay. And then for cotangent, a couple ways to think about it. You can think of cotangent as 1 over tangent, and just remember when tangent is equal to 0, that's when x is 0, pi, 2 pi, so on and so forth, k pi, where k is an integer. Or you can think of cotangent as cosine over sine, and you just need to think about, okay, when is sine equal to 0, right? Just the denominator there. When is the denominator equal to 0? When that occurs, of course, at the same places. 0, pi, 2 pi, up to, k pi, where k is an integer. So that would include like negative pi, negative 2 pi, so on and so forth. Okay? All right. I would ask for questions, but there's no one here because I'm redoing the video in my planning. All right, moving on. Number 4, here we're asking now to determine infinite limits analytically. So in the past, we were just kind of like, well, sorry, in the earlier pages there, we were kind of using the graphs to help us. Maybe your table would help too. But here we're going to do it kind of analytically without a calculator, and so without graphs, without tables. Okay, so looking at, for example, at letter A. All right, we've got that we want to approach the limit, or we want to approach negative 1 from the left. Or sorry, we want to approach positive 1 from the left of this function. And so we can try a direct substitution. If you plug it in straight away, you're going to get something over 0. Okay, so not very helpful to do a direct substitution there. And we can't really factor and cancel. But instead, we can kind of try different numbers. We can basically do what we do with our calculators, where we approach kind of using like decimals that are closer and closer to our number. So from the left, that'd be 0.9, and I did 0.999. Okay, the numerator is kind of always going to be, it's going to get closer and closer to negative 2, right? It's 0.9 squared minus 3 times 0.9. Both of these are pretty close to 1, and so it's going to be basically like 1 minus 3, so negative 2 approximately. But the denominator is where the interesting behavior happens, because 0.9 minus 1 is going to be negative 0.1, right? But then when I do like 0.999, again, the numerator is going to get even closer to negative 2, but the denominator is now going to be negative 0.001. And so as we get closer to x, our values of our limit are increasing without bound. And in fact, we can then safely say it's going to go to positive infinity. Positive infinity because the negative in the numerator will cancel with the negative in the denominator to make it positive. And infinity will, because you can see they're increasing without bound here as we proceed. Okay, as we get closer to that 1 from the left. Likewise, if we change up our limit and approach 1 from the right, okay, now we'll plug in something just a little bit bigger than 1. So I just went straight for the jugular here and went 1.001. Again, our numerator is going to get really close to negative 2. That denominator, though, when you do the 1.001 minus 1, it's now going to be a very small decimal, but dividing by that small decimal makes our overall value really big. We go to a negative 2,000 because that negative 2 is now being divided by a positive 0.001. So negative 2,000. And so we'll say again that it's going to approach now negative infinity, which also we know that means limit does not exist. Okay, quick properties here, and then we'll just talk about these right in here as well. Properties of infinite limits. So if we again talk about c and l and their constants, okay, and f of x and g of x are functions, so that the limit as x approaches c of f of x is infinity. So f is an infinite limit as x approaches c, whereas g of x approaches a finite value L as x approaches c. Okay, if you add infinity plus or minus, or sorry, if you take infinity, you add or subtract a finite number, it's still going to be infinity. Right, if you take infinity and you multiply by a finite number, it'll still be infinity, as long as your number is greater than 0. If your finite limit is negative, then that'll make it a negative infinity, right? For a quotient, if you take infinity and divide it by a finite number, it still is infinity. If you take a finite number and divide by infinity, then it's going to go to 0. Okay, it goes to 0. Okay, this is because your denominator is going to go larger and larger, larger without bound. This number is going to stay the same, and so eventually this whole thing will go to 0. Okay, now looking at some individual limits here real quick. All right, we can kind of imagine here approaching 0, right, in this function. If we approach 0 from the left or right, it's not going to make any difference because we're squaring that. So imagine just like a really, really small decimal, squaring it, it's even smaller, and then 1 over that is going to be ginormous. Plus 1, that doesn't really matter. So it's going to go to positive infinity, or in other words, does not exist. Here for letter B, we're approaching pi over 2 from the right. Okay, again, a direct substitution into tangent of pi over 2. It's going to give us undefined because tangent's undefined at pi over 2. But if we think about tangent in terms of sine and cosine, sine, as you get closer and closer to pi over 2, is 1, right? Whereas a positive 1. Whereas cosine, as we approach pi over 2? Well, it depends on which way we're approaching from. Since we're approaching pi over 2 from the right, that is from values greater than pi over 2, we're going to be in quadrant 2. Cosine is negative in quadrant 2, so this value, though it is small, it will still be negative. And so dividing 1 by a very small number, very small negative number, will make it become a very big negative number, or well, a very negative number. And then times 3 is still negative, so it goes to negative infinity. Negative infinity, because again, cosine of pi over 2 exactly is 0. As you approach pi over 2, though, from the right, you're approaching from the negative side, so this will be negative, but a very small decimal, like negative 0.00001 kind of thing. Dividing by that will make it then a very big negative number, and so negative infinity overall. And then finally here for letter C, the natural log of x. If we remember, the natural log of x's graph looks like that, okay? As you approach 0 from the right, which is the only way you can approach 0 when you're talking about natural log here, approaching 0 from the right, you can clearly see we're going to go down towards negative infinity, and then times 3, it's still negative infinity. And so again, in other words, the limit does not exist. Okay, I hope that was helpful. I know that was really quick, much quicker than I went through it in class, but that's because you have the ability to stop and pause the video if you need to, and rewind and rewatch. If you have further questions, I would suggest you talk with Mr. Widmeyer or Mr. Goff. And then I'm going to turn this thing off here, and hopefully it doesn't fail me again.